guys, hope all of us are doing fine. My name is Ernest, and this is Ernest Sciences and the Mathematics TV channel. In this particular discussion, we're going to look at a way of representing isochoric heat capacity in terms of a partition function. But of course, from this specific wording, we can describe the concept of isochoric as a condition whereby we're going to consider, of course, no change in volume, and therefore we're going to consider an aspect whereby volume is constant. And from our previous discussion, I mentioned the concept of a heat capacity as the amount of heat energy that is going to be, of course, involved in a chemical reaction, whereby this amount of heat is going to raise the temperature of a substance by 1 degrees, either Celsius or Kelvin, so that that's a specific difference in temperature basically is either 1 Kelvin or 1 degree Celsius. So in this case, the nature of this particular conversion is just the same. But we're going to see that basically there are other kind of wordings that we have used for the molar heat capacity, which is going to limit us to use a specific quantity of substance, which basically involved the use of a mole. Now in this particular case, we are going to consider the heat capacity at constant volume. And from our previous discussion on the concept of the relationship between molar heat capacity at constant pressure and volume, we had considered the case of giving this in terms of a C subscript P for constant pressure and molar heat capacity at constant volume given as such. And in this case, we're going to consider this specific aspect of heat capacity in terms of a constant volume. And in our representation, we are given it in terms of course, this was sigma QV, and then that's a derivative with respect to, of course, temperature given as dt. So this was our formal representation of this molar heat capacity in terms of constant volume. And therefore, in this case, we're going to consider the aspect of internal energy, since we have defined it elsewhere in our representation of a partition function. So that is going to be convenient for us in representing this heat capacity or isochoric heat capacity in terms of a partition function. And therefore, this is going to give us a version of the CV equivalent to the partial derivative of internal energy with respect to temperature, and this is going to be under constant volume given as such. So basically, this is an analogous expression of this one, but in this case, we are going to consider the aspect of internal energy, as I said, so that it's going to give us a substitution for U, which we have defined elsewhere in some of our discussion. So in this case, we have defined the change in internal energy using a partition function as a product of this Bond's Newman's constant the square of temperature, and of course the derivative of Q, or the natural log of Q with respect to temperature. And we said this basically happens under the condition of a constant volume given as such. So this is going to be a derivative, a substitution that is going to form our, of course, numerator at this specific point. And in this case, I've discussed on various laws of derivatives which are mentioned, and whereby we're going to consider now in this particular case an aspect of the product law which are given in our first representation. So therefore, we're going to consider these two specific aspects, whereby we're going to have the kBt squared acting as a unit, and therefore a unit, and therefore we're going to have the partial derivative of the natural log of Q with respect to T V given as a unit. And therefore, I've said that if this unit represents U and V, I can just simply put let U be represented by kBt squared. So I'm just definitely doing this in order for us to find a convenient way of using a correct derivative. And let the natural log of Q with respect to temperature at constant volume be given as V. So for us to find the derivative of this specific product, we have said that we're going to use this product rule, which states that we are going to hold one constant and do a derivative of the first one, and then we're going to hold another one constant and do a derivative of the other one respectively. So I've put this one in terms of U as a constant and dv over dx. So I've done a derivative of the second one and held the first one constant, and then I'm going to have that one as a sum over d U over dx given as such. So in this case, I've held the one that was held constant. Of course, I've held this one that was derived in the first, of course, element of this specific expression constant, and I've derived the one that was held constant in this specific case with respect to x. So therefore, that's going to give us a clue of representing this specific derivative of u with respect to temperature in this particular substitution, whereby we're going to consider this one, particularly the aspect, the right side of the equations, these ones are equivalent. We're not going to substitute with this as other u. So I'm going to consider this one as a substitution for u, and therefore, as we are going to derive this one with respect to temperature, therefore, I'm going to use this particular product rule by considering kBt squared and then this one as a second aspect of this. So I hope that that product rule has been taken into account. So therefore, I'm going to just do away with this so that we can have enough space for us to do that specific derivative. So we're going to have the CV represented in terms of, so let me just quote this formula here so that we do not forget. CV is equivalent to the partial derivatives with respect to u constant volume. So we're going to, of course, have this substitution for u, and therefore, as we said, this is going to be given in terms of, we have this partial derivative of, this is b the square of t, and then the natural log of t with respect to temperature at constant volume, and that is going to represent our numerator, of course, and this is going to be with respect to dt given as such. So I decided that we're going to choose this one as a product of two, of course, numbers or elements, whereby I've chosen this specific section to be u. So I'm going to consider this derivative of kBt with respect to dt, and then next I'm going to consider v, representing this specific aspect in brackets, the constant volume. So this is going to represent the CV, which is equivalent to, so I'm going to derive this first one, which is of course representing v. Let me start, I can start with v. I'm going to derive this particular first one. So in this case, this is going to represent u, and this is going to represent v in that specific respect. So I've started with, let me hold the u constant, which is going to be given as this one, and then I'm going to derive v in that specific respect, or perhaps I can just change, because of the orientation of this one, I can just interchangeably put this one as u, and this one be in that specific case for us to appropriately represent this one. So this is going to represent my v, and this is going to represent my u at this specific respect for us to apply this specific formula. So we're going to have u, which is basically this specific part held constant, and we're going to derive v with respect to x. So my v is representing this one. So therefore, for me to derive this, to do a derivative of this one with respect to temperature, I'm going also to consider this one, which is going to be, of course, 2 kBt as my first set of that specific derivative. And I'm going to hold this one constant, therefore it's going just to remain the same value of this one with respect to volume given as such. And I'm going to have the sum of that one, and I'm going to hold the v constant. Now in this case, my v is this specific aspect of kBt squared, and then I'm going to do a derivative of this specific aspect of u given as such, and this is going to give me, of course, the second derivative of this specific aspect, whereby I'm going to have this one as the square of d natural log over q, and then I'm going to have the square of that specific aspect of so this one is a derivative with respect to temperature, and not to, so we're going to consider a derivative with respect to temperature, so it's going to be this del over del t given as such, and this is going to represent that particular equation given as such. So this basically is a representation of the isochoric heat capacity, and it can be given in various forms, as we're going to see in some of our discussions, especially when we're going to consider these other definitions in terms of perhaps an ensemble average, and of course writing it in terms of different terms of the mean squared, and of course the square of the mean of internal energy in that specific aspect. So perhaps catch us in our next video where we're going to look at a different version of this, and that's going to form a closing part of this representation for isochoric heat capacity. So that is it for now. Kindly check our description boxes for various links of other videos which are related to this. So bye, God bless you. Catch us in our next video.